In this video, we are going to discuss applied expected value calculations. In short, we've already looked in class about how to calculate expected value. That's not what this video is about. This is just saying, let's see some further values and see how expected value ties in. Our learning objectives are to understand what a fair game is, and also to be able to analyze a game by building a probability model and calculating the expected values from scratch. Please remember, when we first started doing expected value, you were already given the probability model. There was nothing there that you had to figure out. It was just the number crunching component. In this one, you will have to figure out some components of probability. Short version, the motivation behind a lot of this is actually casinos. Everybody knows that a casino needs to make money because, well, every business needs to make money. But casinos are in a somewhat unusual position. The more that the player loses, the more money that the casino wins. So every casino game has to be set up so that the house is going to win more often than the player. But the casinos can't rig it with really, really high probability because, well, if they did have the games rigged so that they won virtually all the time, their expected value for every game would definitely go up. They would win very large amounts of money for every time somebody played. But that's the problem. People don't like losing large amounts of money, and they absolutely hate losing large amounts of money really, really fast. So if the casino is winning too much money too fast, people will walk away and they'd never come back. Short term, that's great for the casino, but in the long term winnings are going to go down because of bad attendance. If people just never come back, you're going to have people, new customers in all the time, and that's very difficult. So no matter what the odds are, whether it's a high probability or low, casinos can't make money unless they keep people coming through the doors. They have to have people who are willing to come back and keep gambling even after they've lost money. In order to do that, you have to set up the games so that there are winners, and sometimes there needs to be big winners. When people can see that others are winning all around them, it makes them feel like it's only a matter of time before they start winning too. And that's what's good for attendance. In fact, I would bet a lot of money that somebody in the room knows at least one person that's won at least a couple of $1,000s at our local casino, and I would not be surprised if every single one of you knows someone who had won money at a casino. I mean, we've got the casino only 4 miles away, so a lot of the things that we're going to be working on today combine the ideas of calculating probabilities from Unit 2. Remember, that's creating the probability model, that's compound and or probabilities, it's given probabilities, it's mutually exclusive, it's independent, it's the tree diagrams, it's all of that stuff. Combine what we know about calculating probability with our formula for calculating expected value. And we're going to check to see, is this game fair, yes or no? So let's start here. A bag has 10 red marbles, 8 blue marbles. The player reaches into the bag, pulling out 2 marbles, one after another, without replacement. If the color of the 2 marbles matches, the player wins $10, but if they don't match, the player wins nothing. The game costs $5 to play. Now, before we start the work, please note, feel free to pause, feel free to backtrack, rewind the video, whatever you need to do to help you out. Use a tree diagram to help find the probability that the 2 marbles match. Okay, so since we're building a tree diagram, we'll start off and say, option 1, what could happen? Well, when you make your first pick, you could get a red marble or a blue marble. Red or blue. Those are the only two options at first. Remember, each branch along our tree, though, we want to write down the probability. Well, if we have 10 red marbles and 8 blue marbles, how many total marbles are there? 10 plus 8 would give us 18. So there are 10 red out of the 18, 8 blue out of the 18. That's our first level of the tree diagram. This is what happens for pick number 1. But you've got to pick another marble. And what's going to wind up happening is you will either win or you will lose. In this particular branch, you win if you get a red marble, but you lose if you pick the blue. On the other one, you're going to win or lose just the same, but on the branch to the right, you win by getting a matching blue, but you lose if you pick the red. So let's write out the probabilities along the way. Please note, this is being done without replacement. So the marble is not going back in the bag. After you pick a red marble, well, there are no longer 10. One of them's gone, so that would leave you with 9 marbles out of the 17 that are left. But there would still be 8 blues out of those 17. On the other side, well, if we picked blue for the first marble, that means there are only 7 left out of 17, but all 10 left out of the 18 red. I'm sorry, 17 red, because we took one out. Well, please note, we have 2 different paths for winning. You would be able to win if you had 10 out of 18, followed by 9 out of 17. Red followed by red. So winning is 10 out of 18 times 7 out of 17. 10 times 7 gives us 70. 18 times 17 equals 306. And I know, even if you're following along with the calculator, you're probably not getting the numbers as quickly as I was. That's fine. For our other path to winning, 7, we had 8 blue out of 18, followed by 7 blue out of 17, which gives us 56 out of 306. And so when we're looking at this, ultimately, to build the probability model, well, you can win or you can lose. If you win, you get $10. If you lose, you get nothing. The probability of winning is the combined 70 for option 1 plus the 56 for option 2. That leaves us with 126 out of 306 ways to win. And simply taking 306 minus 126, that leaves us with 180 ways to lose. And so here is our probability model. The amount of money you win, the probability that you win, and this box is part A. Part B, is the game fair? Well, a fair game means you are going to wind up not making money, not losing money in the long run. So that way you're not robbing people, you're not losing money. It's fair because both the player and the person who runs the game have basically, in the long run, they're not robbing anybody. It's fair to both. Well, in order to do that, in order to answer whether or not it's fair, a lot of that's going to be based on the expected value. So for part B, we need the expected value of this game. Well, we'll take $10 times 126 over 306. And that's going to be 1260 over 306. 0 times 180 is 0. And so to get our expected value, we've just got to crunch those numbers. We wind up with 1,260 over 306. And converting that into some money, rounded to the nearest penny, we'll take 1260 divided by 306 and get $4.12. So the expected amount of payout, the expected amount you win when you play, is $4.12. But the game cost $5 to play. So if you have to spend $5 to play it, and then you win $4.12, that means there's an 88-cent difference. Well, did you win money, or did you overall lose money? Well, this one, you're spending more than you got, so overall, for the player, they have lost money in the long run. So is this game fair? No. The person running the game is going to make money in the long run. It's not fair because of that. So what should the value of the game cost in order to be fair? Well, for it to be a fair game overall, you need an overall loss or win of 0. The winnings are going to be $4.12, so overall it should cost $4.12 to play, rounded to the nearest penny. Okay, you have a couple homework problems that are based on this game of greed. A big part of being able to answer those questions is going to revolve around the idea that you understand the game. So replay the video a couple times if you need to, pause it, rewind it, whatever, but make sure you understand what this game is doing. The game of greed is a game of chance in which players try to decide when they will have accumulated enough points on a turn to stop. You will roll 2 6-sided dice, and you get to keep the amount that's showing on the 2 dice added up. After every roll, you have to decide, will you roll again, which would add to your current score, building it up higher and higher, or do you stop and put your points in the bank? The catch to the game is if you roll a total of 5 on the dice together, you get 0 points for that entire turn. For example, if the first roll is a 9 and you decide to roll again, the next roll has a 7. So 9 on the first plus 9 on the second give you a total of 16. And then you decide, do you want to put the 16 in the bank or risk keep playing and losing? If you decide to keep playing and then roll a 5, you get a score of 0. Well, here's the situation. A person is playing greed, has accumulated 26 points so far. Should they keep playing, yes or no? Well, a lot of that is going to depend on expected value. If we can calculate the expected value of their total score with the next roll, then we could say if it's higher than 26, it'll be to their advantage to keep playing. But if the expected value starts going down and is less than 26, then that means it's not to their advantage and that they should stop. Please consider the example. You'll note on the left how we have the 6x6 grid that we used a lot back in our first unit. It has the sums. Obviously, you can see you roll a 1, you roll a 1, it adds up to 2. You roll a 5, you roll a 4, it adds up to 9. Okay. Please note, any of these 5s, those are all the ways in which you lose and get 0 points. Well, consider the probabilities then. Sorry. There's only one way to get a 2. So the probability of adding 2 points, 26 plus 2, to get a total value of 28, there's one way out of 36. In order to get 3 points, we're noting that's a probability of 2 out of 6, but 3 more plus the original 26 would mean 29. For the 4s, the probability is 3 out of 36, and so 26 plus 4 gives us the value of 30. Please notice what we're doing is building the probability model by using the sum 26 plus the number. That will give us the value. But we're also taking the probabilities and listing them out. The important part, though, is this next one. If somebody rolls a 5, the 5 is the losing option. If you roll a 5, you lose the 26 and you're back down to 30. You're back down to 0. And there were 4 out of 36 ways to do that. Continuing further, though, for the 6s, you roll a 6, you're okay. That had a probability of 5 out of 36. And of course, 26 plus 6 gives us the 32. So you can see, continuing this pattern with 7s, with 8s, with 9, with 10, with 11 plus 12, that's where the table's coming from. All right, so this is our probability model. I highly recommend that you pause right now and write down a chart similar to this with the probability models, 1 out of 36, 2, 3, 4 out of 36, 5, 6, 5, 4, 3, 2, 1, because this probability, list of probabilities, does not change at all for your problems 3, 4, and 5. The value row in your homework will change, but the probability row does not. So we've got the probabilities. Let's go through and actually calculate the overall. Now, please note, we have to multiply 28 times 1 out of 36. So I'm going to just take 28 times 1 plus 29 times 2 plus 30 times 3 plus 0 times 4 plus 32 times 5 plus 33 times 6. Please note I'm taking option 1 times probability 1 or option 5 times probability 5. 34 times 5, 35 times 4, plus 36 times 3, plus 37 times 2, plus 38 times 1, and adding all of those things up. Please use a calculator. Actually, pause the video, run through the numbers, that way you can see if you're doing it correctly. All of those add up to be the number, if I remember correctly, 1064. Well, our expected value then, because all of these were out of 36, because all of these were fractions over 36, our expected value is 1,064 over 36. And so let's divide that out. And my calculator does it that way. And so we wind up with an expected value on the next roll of about 29.56. Because the expected value is higher than the current score of 26, probability would indicate that the best chance of winning is to keep playing. This is number 3, taken directly from your homework. So, in this one, you don't have 26 points, you have 55. Is it to your advantage with a score of 55 to keep playing? Well, I'm going to go back and take that table, and I want to bring it forward because this is my big tool. What we're looking at doing is not starting off at 26, though. All of these scores that I'm scribbling out were based on the idea that you started off with a score of 26. Well, now we're saying starting off at 55. If you started off with 55, you could have a roll of 2, which brings you to 57. Trying to, there we go. And then you'd have 58, 59, 60, 61, 62, 63, 64, 65, 66, 67. And what we're looking at doing is say 57 times 1. 58 times 2, that's 116. 59 times 3, that's 150, that's 177. Plus, keep going all the way until the end when you're at 67 times 1. Just fill in all the values. Use a calculator. Let's run through and do it. Okay, so mine is 57 times 1 plus 58 times 2 plus 59 times 3 plus 7, 58, 59, 60 times, this is where it's relevant, 60 is where you roll the 5. Rolling the 5 means you get a score of 0. So this piece of 60 isn't what we get, it's actually a score of 0. Make sure you don't create that error because it's not 60 times 4, it's 0 times 4. Plus 61 times 5 plus 62 times 6. Now we're on the back side, so we're saying 63 times 5, 64 times 4, 65 times 3, 66 times 2, 67 times 1, and we wind up with this overall score. When you add them all up, 1,992. Our expected value, again, because it's based on this probability of over 36, is 1992 divided by 36, which we could then take and say 1992 divided by 36 gives us an expected value of 55.33. Or 55 1/3, we can actually tell from the repeating overbar. Because the expected value is a little bit above 55, the current score, it means we are still in a position where rolling again is probably going to be good for us. So it's worth the risk to keep playing. Skipping ahead to number 9, we'll see some of the other ways in which expected value could be used. A prospector purchases a parcel of land for $50,000 and hoping that it has significant amounts of natural gas. Based on other parcels of land in the same area, there's a 20% chance that it's highly productive. Actually, let me back this part up. And I'll switch this to there, highlighter, yellow. 20% chance of being highly productive. 70% chance it's somewhat productive. 10% chance it's completely unproductive. If it's determined to be highly productive, the prospector could sell the land for $130,000. If it's moderately productive, he could sell it for $90,000. And if it's unproductive, he can't sell it at all. Or she. They don't really tell us if it's a he or she in this problem. It's just a prospector. Well, recognizing those pieces is the foundation for being able to say they will have $130,000, and there's a 20% chance of that happening. For somewhat productive, they would sell it for $90,000, and there's a 70% chance, but you get absolutely nothing for this 10% chance. We can use this to get our expected value. Option 1 times probability 1. 130,000 times 0.2. You have 26,000. $90,000 times 70% or 0.7. That is 63,000. And adding on the 0 at the end, well, our expected value, 26,000 plus 63,000, leads us with 89,000 is the expected value for this transaction. But they spent $50,000 to get it. So the expected amount of the sale would be 89,000, but the expected value of the profit, 89,000, subtract 50,000, that would give you a $39,000 profit is what the prospector is expecting based on probability. So did they make a good investment? You bet. If you could wind up making almost $40,000 buying and selling land quickly, you bet that's a good investment. A spinner has 4 colors on it, red, blue, green, yellow, shown here. Half the spinner's red, the remaining half is split evenly amongst the remaining colors. So we should note probability of red is a half, probability of blue is 1/6, green is 1/6, yellow is 1/6. So if the spinner stops on red, where we have 1/2 probability, they win $2. If it stops on blue, they win $4. You notice how I'm building the probability model already writing down my information? If it stops on either green or yellow, they win $5. So $5 for getting green and $5 for getting yellow. So what should the game cost in order to be fair? Well, let's calculate the expected value. 2 times a half is a 1. 4 times 1/6 is 4/6. 5 times 1/6 is 5/6. 5 times 1/6 is 5/6. But of course, 1 back at the beginning is 6/6. So when we add up our expected value, 6 plus 4 plus 5 plus 5, that's 20/6, which is $3.02, which rounded to the nearest penny is $3.33, with an expected payout of $3.33. In order for the game to be fair, it's got to cost the same amount to win as to play, $3.33. Number 15. This one is in the review questions for the section. You'll remember that this is not based on the new material, but based on something we had done previously. Consider the partially completed probability model. What is the value of x? Well, x is here in the probability. Probability has to add up to 1. So all of these numbers in this row must sum to 1. 0.25 plus 0.15 is 0.4, 0.40, plus 0.05. Those together are 0.45, so we're saying x plus that has to be a total of 1. That tells us x is 0.55, which is 55%. So what is the expected value now? Now that we know x is actually 0.55, well, option 1 times probability 1, that's 1.1. Option 2 times probability 2, 4 times 0.25 is 1. Option 3 times probability 3, $7 times 15%, that's 1.05. And lastly, option 4 times probability 4, 11 times 0.05 is 0.55. So adding all of those up, 1.1, 1.0, 1.05, and 0.55, adding up our different options, we wind up with an expected value for choice B, or number B, letter B, question B. The expected value for this situation is $3.70. And the last one we have. A student does not have enough time to finish a multiple choice test, so they have to guess on the last 2 questions. List the sample space if the only choices are A, B, C. Lots of ways of doing this. Creating a sample space, we could say we have choice 1, choice 2, choice C. And we could do a tree diagram saying A, B, C, A, B, C, A, B, C. This is one way that we'd be able to create our list by following through with the tree diagram. We also saw that you could use logic. A with A with B, A with C. This lists all the different ways that you can have A on the first, and then run through the options on the second one. These would be the options for having B on the first question, A, B, C for the second. And likewise, third one could be C's. A, B, C are the options there. So here's our sample space. We have this list of 9. Please note, and remember the learning objectives. What is a fair game? A fair game is one in which either side of it isn't going to make money off the other in the long run. It's not the casino, it's not the player. There's no advantage to either side. So in the long run, it's fair to both. Can you calculate probabilities to create a probability model? That was our Unit 2. And then combine with the first part of Unit 1 to calculate expected values. If you can calculate expected value by using a probability model you have built, then you've met the learning objectives for this particular unit.